Multiplying numbers gives you magnitude, but multiplying vectors can capture something much more interesting: area, volume, and spatial orientation. In standard linear algebra, the mathematical tool we use to calculate this n-dimensional volume is the determinant. The determinant is restricted to the top-level dimension of a space. It represents the peak of a broader landscape of multilinear functions that describe geometric dependencies at every intermediate level. To understand these relationships, we have to extend our standard vector spaces into a new algebraic system, one where multiplication natively encodes these geometric properties at every scale. The formalization of this concept is detailed in Kenneth Hoffman and Ray Kunze's seminal text, Linear Algebra. It was here, in the mid-century academic halls of MIT, that mathematicians championed this rigorous level of algebraic formalization. Mastering these multilinear structures requires us to leave basic geometric intuition behind and construct the Grassmann, or exterior algebra. On the right side of this board, we are building the exterior algebra. The operator that drives this space is the wedge product. This equation defines the fundamental axiom of the entire algebra. It is the alternating property. Wedging any vector with itself equals 0. Geometrically, if you try to span an area using the same line twice, it collapses into 0 area. We can test the algebraic consequences of this rule by wedging a sum of two vectors against itself. By definition, this must also equal 0. Assuming the wedge product is bilinear, we can expand this expression into 4 distinct terms. Applying our alternating axiom, the self-wedged terms, v wedge v and w wedge w, evaluate to 0 and drop out. We are left with v wedge w plus w wedge v equals 0. Rearranging the terms reveals a strict relationship. V wedge w equals negative w wedge v. This single algebraic rule enforces spatial orientation. Swapping the order of vectors mathematically flips their sign, preserving the spatial direction of the area they span. Now we escalate this logic from individual vectors to abstract multilinear forms. The challenge is determining how to multiply an R-linear form, L, and an S-linear form, M, to produce a new alternating form. The initial approach involves taking a standard tensor product of L and M and mapping it into an alternating space using a projection operator, pi. To see if this operation behaves predictably, we have to test it using standard coordinate functions. If we group the operation on the left, multiplying the form dij by fk, the expansion yields a specific projected tensor arrangement. Grouping the operation on the right, multiplying fi by djk, yields a second expansion. For this algebra to function, the multiplication must be associative. The order of grouping should not change the final output. But when we compare the two derivations, the equations do not balance. Without associativity, the structure collapses. The operation cannot reliably string multiple forms together. The fix requires us to account for overlapping permutations. We must introduce a combinatorial scaling factor based on the degrees of the forms. The tensor product of an R form and an S form overcounts permutations that are already internal to L and M. To find a product that respects the total symmetry of the combined space, we must divide by those internal R factorial and S factorial redundancies. Scanning by this specific combinatorial ratio normalizes the product across different groupings. It ensures that the final alternating form is identical regardless of whether we multiply L and M first or M and N. With an associative product established, we have the mathematical glue required to unify separate alternating forms into a single space. We can construct a graded ring that aggregates every possible dimension of multilinear forms over a given vector space. This equation is the Grassmann ring. It is formulated as the direct sum of all the alternating form modules from degree 0 up to n. At the lowest levels, A0 represents the base field of scalars, and A1 represents standard linear functions, or one-vectors. Moving up the ring to A2, we find bivectors, forms that evaluate two-dimensional areas. The structure culminates at AN, the top-level module, which calculates complete n-dimensional volume. If you attempt to wedge more than n vectors together in an n-dimensional space, the vectors are mathematically guaranteed to be linearly dependent. Because linear dependence combined with the alternating property forces a 0 result, the Grassmann ring naturally bounds itself. It builds upward and precisely terminates, creating a closed mathematical architecture. we can apply the machinery of this ring to one of the most complex computations in linear algebra. In example 13, Hoffman and Kunze use the exterior product to derive the Laplace expansion. The scenario requires evaluating the determinant of a large n by n square matrix. We start by defining an R-linear form, L, that operates on a selected R by R submatrix. We then define an S-linear form, M, handling the remaining complementary block. To calculate the total determinant, we merge these subforms using the wedge product. Both L and M are alternating forms, evaluating the permutations of their respective row and column indices. By wedging them together, we are mathematically reconstructing the complete determinant function, D, for the entire matrix. This reconstruction relies on the exact definition of the wedge product we used to secure associativity. That definition demands a combinatorial summation over all distinct cosets of permutations for the combined indices. That mandatory permutation summation over the submatrices is exactly what the Laplace formula is. The compact exterior product notation expands directly into the traditional Laplace summation. The Laplace formula identifies the determinant as the exterior product of its subblocks, evaluated through the ring's coordinate functions. Beyond the raw calculations, the true elegance of the exterior algebra lies in its core axioms. The Grassmann algebra translates geometric area, volume, and orientation into a strict algebraic language. It relies on two foundational pillars. The product must be bilinear, and it must be strictly alternating. From these rules, a unified ring emerges. It provides the structural scaffolding for every multilinear function, placing the determinant within a wider, consistent geometry. If you want to continue exploring the deep architecture of mathematics, leave a like and subscribe for more deep dives into Hoffman and Kunze.